So welcome everybody to another vibrant seminar. And today we have the pleasure of having Eric Naslund, if I say it right. Okay, talking about chromatic numbers in Euclidean space. Eric.
Great. Well, thank you so much for having me. Today I'm going to talk to you about the chromatic number of Rn with multiple forbidden distances. So let's get started with maybe the classic motivating problem, or one of the oldest problems in this area, is the Hadweger-Nelson problem. And I'll just remind you all, I mean, probably you know what it is, but it's what is the minimum number of colors we need to color the plane so that there are no 2 points at distance 1 that share the same color. And we denote this minimum number of colors by chi of R2. So we're going to be using that kind of notation throughout. And this problem, for a very long time, the best bounds were, it was at least 4 and it was at most 7. And these are kind of pictorial representations of why it would be at most 7 and at least 4. And in the last several years, there was an improvement by a researcher who is well known in longevity, not really in mathematics, but in longevity research. Erdös gave an improvement to the lower bound. He constructed a 1,581 vertex graph that showed that the chromatic number of the plane was at least 5. And so that's where the bounds stand today for this classic problem, where I think a lot of people believe the hexagonal tiling that gives you this upper bound of 7 is probably correct, but it's still completely open. So along these lines, we can ask about the chromatic number of higher dimensional space. So this exact same question, let chi of Rn denote the minimum number of colors required to color Rn so that no 2 points at distance 1 have the same color. And a maybe surprising fact was that this quantity, so we can ask about the growth rate and how fast it grows, but this quantity, it turns out, grows exponentially. So for very large n, it was first shown by Frankel and Wilson, and the best bounds today are what's given below. The upper bound of 3 is given by Larman and Rogers, and that hasn't been improved since 1977. And the lower bound is due to Rygorodski, and that's also about 24 years old. The way these bounds work is they're actually an application of the polynomial method. So all exponential bounds for this problem use the polynomial method in some way, and we're going to explore that as we go on. But I just wanted to mention that before Frankel and Wilson used the polynomial method, there was no exponential bounds and all exponential lower bounds. So in this talk, we're going to focus on questions surrounding the lower bound. The upper bound approach is quite a bit different, and often uses a different kind of argument. Okay, so Erdös had asked a related question, which is, what if you have multiple distances instead of just one distance? So we can define a graph, G sub A of Rn, where we have a, the vertex set is still Rn, and the edge set is given by points where their distance belongs to some set of distances that we've set up in advance. Now the question is, what we can do is we can define the m distance chromatic number, which is the chromatic number of Rn, the maximum number we need for all distance sets. And this is something that Erdös looked into or asked about. And he was, I think, particularly interested in the plane. He wondered whether this number grew polynomially, and more generally, so what does that mean is, does it grow polynomially in M? So does the chromatic number of the plane with multiple distances, as we add more distances, does the minimum number of colors, how does that grow? And he asked more generally, can we determine this for Rn, for any M or any distance set? He was he asked about these problems. And I'll just briefly say that very little is known about the plane. Erdös noted that it goes to infinity as m goes to infinity. And I might just pause here for a second and ask, does anyone have any questions so far about the definition of the m distance chromatic number? Okay, if not, I'll continue on. I'll just briefly say that the argument Erdös had to notice that the m distance chromatic number of the plane grows faster than the number of distances that this quantity listed below goes to infinity. The way he noticed that was just by observing that the n by n grid has at most m divided by square root log m distances. This is the Landau square number of things that can be written as a sum of two squares. So if we have an n by n grid and it has at most, n squared over square root log n distances in it, that means if I have that set of distances, then that set of points is a clique. So because it's a clique, every single point needs to have a different distance. So in fact, what Erdös noted wasn't just that this goes to infinity, that it is at least m times square root log m. And in fact, that's all that's known about the plane. No better bound than this. Well, you can use a hexagonal lattice and it gives a slightly better bound, but nothing else is known. And the upper bound is 7 to the power of m. It's quite large. So this is a problem that Erdös had asked about a long time ago, and the bounds are completely unchanged from whenever he asked it. So we can ask about what happens for higher dimensions with m distances. And what we have is, if you allow more distances, there's a way to kind of iteratively apply the Larman-Rogers bound and just exponentiate that bound. So every time you add an extra distance, you can just take the Larman-Rogers bound of 3 to the n and take it to a higher power. So you kind of get this trivial upper bound, or it's not trivial because it requires Larman and Rogers work, but moving it over to the m distance case is not very hard. So we get this upper bound of 3 to the m times n, which is just, and we can ask about the lower bounds for the chromatic number. And there were some lower bounds of Bernardikov showing that it grows exponentially well, we know it has to grow exponentially times a constant, but the kind of thing that we want to know about is how does it grow as a function of m? And we get something that looks like m to a power to the power of n. And it turns out for some distance sets, this is the truth. And so we'll see that. So what we can show is we can show a kind of more precise lower bound that it grows at least times a square, it's like square root m to the power of n. So this is the lower bound that we show. And the constant is a specific constant that comes out of the Poisson summation formula. And it turns out that's kind of interesting. One thing I think is kind of interesting is that, I should also say this bound improved or improves the best lower bounds for fixed m, and disproved a conjecture of 4 other mathematicians that have worked on this problem. So it turns out that this is actually about correct for the very specific distance set of square root 1, square root 2, square root 3, all the way up to square root m. Now this is the distance set that comes out of having the integer lattice. So it's a particularly nice distance set. But when we have this distance set, it turns out we have an upper bound that's also of the form square root m to the power of n. So the overall result is that if you ask to color Rn, and you require that points that are at distance 1, square root 2, square root 3, all the way up to square root m, you require that those points are colored differently, then we have then the number of colors you need, we know that it grows like square root m to the power of n, and it's just up to some constant. So here we have a constant of 2 to the n in front as an upper bound, and we had a constant of 0.8 to the n as a lower bound. But the growth rate in m is determined. And so this upper bound is due to Kupovsky, and the upper bound is a kind of sphere packing argument. Basically, you can use some kind, just a random lattice and make some spheres around each of the points. And if you make the spheres really small, you can shift it, and it looks a lot like that hexagonal lattice we had at the start. It's actually the same idea as the hexagonal lattice for the original Hadweger-Nelson problem, is to get this upper bound. But it's kind of a multi-dimensional version. Okay, so yeah, we end up with these bounds that we have the right dependence on m in this case. Okay, are there any questions so far at all about the statement of the results? So continuing on, the results will actually also apply to cliques. So you can ask about cliques in the graph. So we'll let chi sub k of g denote the minimum number of colors needed to color a graph G so that no color contains a k+1 clique. So this is very similar to the previous thing. We instead of wanting no color to contain an edge, we want no color to contain a clique, which is a slightly more restrictive thing. So as before, we'll define chi sub k of Rn for a distance set A as just chi sub k of that graph GA of Rn. Whereas before, GA of Rn is the graph with vertex set Rn, and where two vertices are connected if their distance is in our distance set A. And we'll put a bar on top to denote that it's the maximum over all possible sets of size m. I'll note a couple things about the history. Frankel and Roto proved that chi sub k of Rn grows exponentially. So if you just have one distance, the number of colors you need to color the Rn so that there's no clique of the same color, that also grows exponentially, which is maybe kind of surprising. For the equilateral triangle, we can get better quantitative bounds with the slice rank method. This is and I'll note that Bernardikov also has some lower bound results for when m is going to infinity in some ranges when we have multiple colors. So our main result using the partition rank method also applies to these cliques. We just have a slight adjustment. Before we had this constant gamma chi times square root m plus 1. Now you just divide the square root m plus 1 by k. And one thing I'll note that so we do expect the bound to be smaller because it's a little bit harder to have a clique, but I will note that this is not a lot smaller. So this is maybe a little bit surprising that the growth rate in k is not too severe, because some of the other methods to get bounds with higher cliques end up really hurting the quantitative bounds. Okay, so in fact, the exact same method will give this, whether we're using the other method uses the polynomial method. Here it's the partition rank method, which is a kind of higher dimensional polynomial method. And so what we'll do next is we're going to overview the partition rank method. So it's kind of a multivariable version of the linear algebraic method. And it's needed to get these good bounds on k cliques. It was introduced by myself in 2 papers, and following the work of Tao. So Tao introduced the slice rank, and for some of these problems where we have to have where we need a little bit more flexibility, it's important to have the partition rank, and particularly for this kind of clique finding problem. And one other note is the slice rank, the tensor rank, the slice rank, the matrix rank and the partition rank are all the same for 2 tensors. The slice rank and the partition rank are the same for 3 tensors, and for 4 and higher, they're all different. So let's get into what is the partition rank and what is the linear algebraic method. Okay, so I'll just briefly note the linear algebraic method is this kind of, I'll just say this, it's a version of the polynomial method where at the end of the day, we just note that a particular matrix has a certain rank, and that's how we end up getting a bound for a problem. And so, so let's talk about tensors. So for finite sets, we'll refer to a function f from the Cartesian product of these sets to any field f as an order n tensor. And this might not be the definition people are used to. People might be used to a definition of a tensor that involves a multilinear form, but these definitions are actually the same if you think of this definition here, where this function f is sort of like the elements of the matrix. So this can be thought of as like whatever the size of x1 is, up to what the size of xn is, we have kind of a grid of elements of fn. So when n is 2, we'd call this a matrix, and when n is 1, we'd call it a vector. And to think of your tensor as a multilinear form, it's you take your vectors and you do kind of some sort of, you have this grid, this rectangular grid of numbers, and you do a kind of operation where with that rectangular grid of numbers and with your different vectors to get your multilinear form. Okay. So just some basic examples. So just to repeat kind of what I said, with this notation, a matrix with entries aij is a 2 tensor. And the way I'm kind of writing it in the previous thing is it's like we have a function f from these sets. X are index sets approximately. So we have like f is a function from 1 to L, cross 1 to L, and it goes to our field. And the ijth entry, or f applied to ij, is just aij. So the function f, really, you can think of it as just the aij. It is the matrix. And a rank 1 matrix corresponds to a 2 tensor, f from x cross y to f, where we can write f of x, y is equal to u of x, v of y for some functions u comma v. And this is the same thing as an outer product. So with our notation. So yeah, so a rank 1 matrix is just when I have like a vector u, outer product vector v, and it's the exact same thing in the function notation as a u of x times a v of y. So when we define, and I'll just recall that when we define matrix rank, we actually ask to write it as, we ask how many rank 1 functions do I need to write what is the minimum number I need to write the matrix as a sum of rank 1 functions. That exact same idea is how we'll define the partition rank. Okay, so if I have a function h from this Cartesian product of index sets, x1 all the way up to xn, and this function goes to a finite field f, or sorry, to some field f, it doesn't have to be finite. We say that it has partition rank 1 if it can split in any form at all. So if I can write it as a function of some set of indices, xs1, xs2, all the way up to xsk, times another function of a different set of indices. So for disjoint sets of indices, if this happens and these sets are non-empty, then we say that it has partition rank 1. And we define the partition rank of some function on the Cartesian product of the sets to just be the minimum r, such that I can, I can write my tensor or my function as a sum of elements who each have partition rank 1. So this kind of, I'm just going to briefly mention again, for whether it's tensor rank, whether it's slice rank, or whether it's partition rank, we always define the rank as the minimum number R such that I can write my function as a sum of rank 1 functions. It's just the definition of rank 1 function is slightly different. So for tensor rank, the rank 1 function has to be completely split as like g of x1, g2 of x2. It has to completely split. For partition rank, we just need it to split into 2 sets of variables. That's all we need. And
do you know if for slice rank, what is the definition?
Oh, yeah, I probably should have included that. For slice rank, it's where one of the 2 disjoint sets of indices has to have size 1. So it has to split of the form g of x s1 times f of all the other variables.
I see, thanks.
So it's like we're slicing off. So for slice rank, it's like we slice off a single variable. And the result is that there are some functions that have full slice rank, the highest slice rank you can have, which is the size of the smallest of the index sets, and functions that have partition rank 1. So we'll see an example later. Okay, so the most important thing about slice rank and partition rank is that the diagonal tensor has full rank. So if we have a finite set x and we take the k-fold Cartesian product of x with itself, and we look at the function f from x to the k to some field f, and it's the diagonal tensor. So it's the diagonal identity tensor. So that means just it's 1 when they're all equal and 0 otherwise. There's no way to write this. So we can write this thing kind of obviously as a sum of size of x different functions, because you could just have the function that is 1 when x1 is 1 and 0 otherwise, and the function that's we can just go through every element of x and use these kind of indicator functions. But the thing is, there's just no better way to write this. No matter what, the partition rank of this thing will be at least x. And that's kind of, this is what a lot of the applications of it hinge on, because for various applications, we're going to find something where we have a diagonal tensor. And once we have a diagonal tensor, its partition rank has to be maximal. And I will just briefly note, the diagonal tensor can have different non-zero constant values at each thing. So at each element in X. So in this slide, I said it's 1 everywhere. It could just, as long as it's just some non-zero value at each, that's okay as well. So this is kind of the important lemma. And now we're going to see, how does this apply to what we've talked about so far? So our kind of starting point is we take some subset of Rn, and we suppose that a subset of this, so we want to restrict Rn to some set that we can work with, and that's kind of it's like a universe set. That's our bigger set S. And then we take some subset of that, A, and we say, suppose that A doesn't have a k+1 clique. And suppose that, and so then what we'll show is so then suppose further that that means that this size of the set A is at most some constant C. Okay, so this is kind of the world we're going to set up. The way our proof is going to go is we're going to choose S really carefully to prove that any subset of it of size can't have a k+1 clique. But if we have this kind of result, if we get to a result like this, where we have some subset S and every subset of S that doesn't contain a k+1 clique is small, this will bound the chromatic number of Rn. So let's see what I mean by that. If each color used to color S can have at most C different elements, because S is a subset of Rn, to color Rn, we also have to color S. And each color used can't have more than C elements, because we know that if I have more than C elements in S, then I have a k plus 1 clique. So I've broken what I wanted. So what we need, so it follows that the chromatic number will have to be of Rn will have to be at least the size of S divided by this constant C. So this is kind of the framework in which these proofs work. I'm just going to take one other note here is I kind of mentioned two results at the start for just the chromatic number and then for k plus 1 cliques, but the proof for both is the exact same. We just use the partition rank, and a person could think of it as a different proof when in the case of single distances, because the partition rank is now just the matrix rank, but it's just the exact same proof, just goes through for all of it. We don't need to rewrite it twice. So I'm just going to talk about k plus 1 cliques going forward. So this is kind of the setup we want. We want to have we want to find a set S in Rn and prove that every subset of it that doesn't contain a k plus 1 clique is small, because that will bound our chromatic number. And the next thing we do, so here's where the partition rank enters. So this set S, I'll just for some context, it's just going to look like a square box of integers where we choose that box carefully down the line. But it's just going to be like it's just going to be a box of integers, 1 to L to the power n. That's what it's going to look like. So it's going to be very simple. And so for this box of integers, so it's going to be a box, and we're going to have L as a parameter that will fit, and we'll be a little careful about that. Or sorry, it's going to be a subset of the box of 1 to L in a careful way. I should be more precise. It's going to be a subset where each element, anyway, we'll see that in a second. It's not a very complicated set. But the thing is, for our set at S, what we'll look at is a tensor on S to the k plus 1. And we're going to suppose that we can construct this tensor so that it's non-zero when all of the x1 up to xk are equal, and 0 whenever they do not form a k plus 1 clique. So if x1 up to xk plus 1 do not form a k plus 1 clique, I want this tensor to be 0. If they do form a k plus 1 clique, I don't care what it is. It can be anything. But if they don't form a k plus 1 clique, I definitely want it to be 0. And what happens then is any subset A of this larger set S that doesn't contain a k plus 1 clique, if I restrict my tensor to it, I look at the tensor restricted to A cross A cross A cross A, that will have to be diagonal because A doesn't contain a k plus 1 clique. So every element 0 except on the diagonal where we insist it's non-zero. So if we can construct a tensor with these nice properties, it means that the largest set with no k plus 1 clique has to be bounded in size by the partition rank. Okay, and I'm just going to mention one other thing here. This is where that lemma about this is where the critical lemma is used. This is where the fact that the diagonal has full partition rank is used, because it's what tells us that when we restrict our tensor to JK, when we restrict the tensor JK to A, that will be a diagonal and will hence have full tensor rank. So if it's a diagonal on a set of size A, its tensor rank is A. This is how we get the inequality. The size of A is at most the partition rank of JK. And I'll add one more. So one other thing is why does the partition rank of JK, why does it work like this when we move down, is if there was a way to write JK as a nice kind of bunch of terms, as a small number of terms, that would still apply when we restrict down to A. That's okay. So what we get, yeah, so are there any questions about this slide at all? This is kind of the important, this is like the, this is the rough overview of how these kind of arguments generally work. And yeah, are there any questions so far? So the only other thing I'll add is there's a book on the linear algebraic method by Babai and Frankel. And roughly it's this kind of idea, but where we use matrix rank instead of higher ranks like slice rank and tensor rank. And partition rank, sorry. Okay, so now the objective is to kind of construct, well, first choose the set S carefully, and then construct this tensor J, where what I want with the tensor is I want non-zero on the diagonal, 0 when we do not form a k+1 clique, and I want to be able to bound its partition rank. These are the 3 things we have to do going forward. Okay, so just rewriting what we have so far, we can, if we have this set S and we have a function JK from the set S to a finite to some field, and the tensor satisfies what I want, then we have this bound. We can put the things together because we know that the partition rank of JK bounds A. That's this equation here. And we know that the bound on A will divide by S. So putting everything together, we end up with this slightly simplified equation. If we find a JK, a tensor with this property and a good set S, then we get this lower bound for chi of Rn. Of k+1 cliques. I maybe should have been a little more precise in the left-hand notation of that equation. Okay, so the way we'll construct JK is, we haven't talked about what distance set yet, but we'll take the distance set 1, square root 2, all the way up to square root m, and we'll define our tensor. So this we'll define fk+1 of x1 all the way up to xk+1 to be 1 when our distances are in this set times a multiple that we'll come back to, and 0 otherwise. So when all of the pairwise distances are in the set AM times a multiplier that's the square root 2p, that's not too important right now, it's to make some of the integers line up. When all of the distances are in there, then this guy will be 1, and when they're not in there, it will be 0. So what happens is fk+1 is non-zero if and only if x1 up to xk+1 form a k-simplex with distances, but it could be degenerate. We could have x2 could be the same as x3. We could have this problem where multiple of the points are just the same. And that's not what we wanted. We want something a little bit better than that, because if multiple are, basically the issue is if x1 and x2 and x3 are all the same and x5 is different, this tensor will be non-zero. But those are not a k+1 clique because they're a bunch of the same point. That doesn't count. So we want to fix that, is the objective. And here's where we kind of need the partition rank, is to fix that. So the tensor JK is, what we'll do is we'll multiply this fk+1 by a special distinctness indicator of tensor that can only be handled with the partition rank. Okay, so that's our next objective. And I'll just mention what we get is an intermediate theorem here. So the way we're going to choose our set S is it's going to be a subset of 0 up to L to the n. It's going to be a subset of the box, but we're going to choose it so that we have exactly Ci copies of element I. So it's going to have the proportion of zeros, the proportion of ones, the proportion of twos is going to be the same for any element in S. So so then what we'll do is we're going to bound the partition rank of JK and optimize over all the choices of Ci. So the bounding of the partition rank is actually going to depend a bit on the set S. And the reason why it depends on that is because this kind of distance function will depend on the set S. The maximum distance between 2 points depends on what points we allow in that box. If we choose a particular subset of the box, we won't have distances that are as large. And so we kind of want a set that has lots of points and not very large, not too many points that are at large distances and things like this. Okay, so when we do this, so what we'll do is we'll bound the partition rank and optimize over all our choices of Ci. we get a theorem that looks like as follows. And I'll explain this in more detail. We'll be able to bound this chi k of Rn with the distance set described before. We'll be able to lower bound it by a maximum of a truncated theta function divided by a sum of 1 plus t all the way up to t to the L minus 1. And there's some elements of this optimization that are a little bit messy. So but the key thing is the way in which we bound is the key thing to note is how do we bound the partition rank of JK? So the important thing is this function fk plus 1 can be written as a product. This particular function can be written as just a polynomial in these distances, because each distance xi minus xj is a sum of squares of the sub-elements of xi and xj. And I wanted to maybe avoid some of this double index notation because it gets kind of a bit messy, and I don't know if it helps with the ideas. But we end up with a sum of xi1 minus xj1 squared plus xi2 minus xj2 squared. And that polynomial, as long as their distances are not above p, we can write the whole thing f as a polynomial in these distances. And when the whole thing is a polynomial, we can just count terms and just kind of carefully count them with a kind of version of Chernoff's bound in probability. So we just write f as a polynomial and literally count the number of terms. And the number of terms we get depends on the proportions of these CIs. And it's just a bit of a messy calculation to calculate how do I, but the size of the set S also depends on the CIs. So we want to do this careful maximization, and we end up with this clean result out of that maximization. So step 1 is write f as a polynomial. Step 2 is count the term, just expand it and count terms. And then step 3 is, now that we have a formula for the number of terms and we have a formula for the size of S, the formula for the size of S is a kind of entropy formula, just maximize it. And we get this thing that looks like this. It's a kind of nice form. But our work isn't finished yet. So we need to actually figure out a couple things, which is what value of K, or how do we maximize, what value of L actually maximizes this? And so for that, we're going to need to use the Poisson summation formula. Also, are there any questions so far? I realize I skipped some of the some details, but it's kind of a bit of a messy calculation. Are there any questions about the idea so far, or what we're?
Yeah. So you're multiplying f by the indicator of the set S. Is that correct?
So. Thank you. That's a great question. We're multiplying it by a function that is 1 when our elements are distinct and 0 otherwise. And it turns out that such a function, yeah, this is a critical point. This really should be, okay. This function that's 1 when they're distinct and 0 otherwise, we can write it as a product of of delta functions. So if you think, so if we looked at the case where it was 3, right? You want to say, I want the thing that's 1 when they're all the same and 0 otherwise. Well, what you can do is you can say that's 1 minus when the first 2 are the same, minus when the second 2 are the same, minus when the first and the third are the same. If I do that, it's going to be something on the diagonal that is just some number that we don't care about too much. It's but otherwise it's going to, so yeah, this is a great question. So we end up with this thing that's like a product of delta functions. And when we get to higher degrees, we're going to have something where it looks like a delta function where the first and the second one are the same, delta and a delta function where the third and the fourth are the same. So you're going to have, so for a 4 tensor, you could imagine this function delta x1, x2 times delta x3, x4. So what this function is if the first and the second variable are the same, and the third and the fourth variable are the same, it's 1, and it's 0 otherwise. That function's partition rank is 1, because it's the product of two functions. But its slice rank is maximal, because it's there's no way to actually separate it.
Mm-hmm.
The reason the slice rank's maximal is maybe hard to explain, but it follows from this blog post of Tao and Sawin. So, yeah.
And this P you didn't mention. How do we choose this P?
So we just choose this P to be such that we want it to just be slightly bigger than the wraparounds that can. So once we have our set S from 0, 1 up to L to the N, we don't want to have 2 points in. We don't want to have 2 points in. We want the maximal distance of elements in S to be at most P. So we choose P to be a little bit larger than that.
Okay. And okay, so then my final question would be, what would S in the end look like? It would be what?
So it's going to look like something. So how about I describe the case of K as 1? It turns out, so what S will be is it's just going to be something where we have some fixed number of zeros, some fixed number of ones, some fixed number of twos, all the way up to some fixed number of L's in every element. Mm-hmm. In every element will just be like, every element is a permutation of every other element. And it's a fixed number of zeros, a fixed number of ones, a fixed number of twos, a fixed number of threes.
I see. And these proportions are all the same, or they're different? They're
all different, and our optimization involves all of them. We have to optimize over all of them. Mm-hmm. So the size of S, what it's going to look like is you have this kind of, to calculate the size of such a set, you end up with like some entropy kind of thing, like it's Ci divided by n. You have this kind of Ci divided by n to the power of Ci divided by n, a product of those kind of thing. So it's a very messy set, and our bound in P depend, or like what P is to be. Basically, P depends on the largest distance between elements in S, so it depends on all the Ci's. To calculate the largest distance is a bit of a mess again. So it depends on all the Ci's. So our prime P depends on all the Ci's, and our set S depends on all the Ci's, and we have to optimize over all of them. And and we optimize the fraction over all of them, and it conveniently comes out to this form below with this truncated theta function. So the truncated theta function's coming from the fact that that's coming from the distances. So the size of the set S is based on the distances between points, and that's coming from the bound for P, which is based on the distances. So, and that's why it has this kind of quadratically growing exponent. Mm-hmm. And yes, we end up with yeah, so maybe I should have given you more of these details. I wasn't sure how much interest there'd be. It's kind of a, I don't know how illuminating a computation it is, but it's, yeah, we have to optimize over all the C, and we end up with this kind of truncated theta function divided by 1 plus, divided by a sum of powers. And then the last thing we have to do is we still actually have to optimize this for L. We haven't chosen L yet. So the way we do that is we'll use so this is what we'll need to analyze, this quantity here. The reason why I've replaced K divided by n plus 1 with gamma, because we just want to analyze it generally. And the way we'll do that is with the Poisson summation formula. So theta of this truncated theta function we can look at a full thing. We can look at kind of carefully, and you can. It's when we use the Poisson summation formula, this kind of comes right out of it. You know, you get the square root of the reciprocal kind of thing. So what we end up having is we end up with a lower bound across all L or we end up that with the maximum across all the L of this quantity has to be at least this funny constant gamma chi. And this constant gamma chi is coming directly out of the Poisson summation. And so this is the last theorem. This combined with the previous one ends up giving us the bound in our main result that we had earlier. I don't know if there's too many questions about the Poisson summation formula. Okay, anyway, so we put this together and we end up with the lower bound for in the main result. And I'll just add one other note that I thought was kind of interesting and was one of the approaches I tried for this problem. The last thing I'll just note is a lot of this result, I told you S is a subset of 0, 1 up to L. It's some kind of complicated subset of a box. It turns out the entire argument, everything about it works if we take S to be some complicated subset of some other lattice. Just any lattice you want, it works. And my objective, well, one thing I'd really wanted to do is I'd wanted to improve on Ragorodsky's bound by trying to use subsets of the Leach lattice or of the E8 lattice. And I couldn't get any of that to work. I was sort of hopeful about it. And, you know, it turns out you can write things about lattices, and you can actually show that if you could improve this gamma chi constant, it has some relation. You can improve some things about sphere packing, but maybe that's just impossible. I don't know. If you can prove gamma chi is bigger than 1, you have a different way of getting some sphere packing bounds. But I don't. Maybe it's not possible. I don't know. So I tried a lot of these things, and I was very hopeful that maybe you could take a different set S, but that did not work. For some reason, for this particular thing, the plain integer lattice seems best, and I'm kind of disturbed by it. So I wrote, if you're interested in that, I wrote an appendix in my paper that's all about just trying to apply it with different lattices and the kind of results you get, and maybe for this problem or the related double cap conjecture. But none of those results led to improvements in the bounds. And oddly, the integer lattice seemed the best. So that's why I'll just leave that as a remark, because it didn't ultimately work. And I left it as an appendix to the paper because I thought it might interest someone. But other than that, so that's how we end up with the main result with the partition rank method. And I'll stop there if there's any questions, because I see we have about 10 minutes left in the hour.
Thank you, Eric. Yeah, so let's open for questions. Do we have any questions? Yeah, I do have some questions. The first would be about the lower bound. Yep. On the theta function.
Oh, sure. Here. Yeah.
I guess that is the best number you can put. I mean, are you actually proving that this is equal?
No. Okay. Yes. So yeah, it's a good. Okay. So if you're asking about
in terms of gamma,
I'll give a bit of a longer answer to this question. So this is maybe kind of, this is actually not always equal. I think it's equal in a regime where this is equal when gamma goes to 0, I think. If you're, you have to be a bit careful about it. But what happens in So if we go to this kind of main result too, if you asked about, let's just say that k was 1, because that's just the regular distances, and I don't know, m was 2 or something, so or 3, so you had 3 colors. The gamma chi ends up actually being a problem. So if you have exactly 3 colors and you want 1 clique, this quantity here, the maximum over L of the maximum over T of this fraction, will be larger than the right-hand side. If you put in any specific gamma, this will be larger than that side. And it's just not, there won't be a nice formula for it. So if you say, I want the number of colors to be 3 and I care about single distances, so k is 0 or 1, then the right-hand side here will not be the best bound. You can just do this maximization and you'll get a slightly better bound. And I think that I mentioned this, there was a disproof of this conjecture of Gorskaya, Mitrichev, Ragorodsky, and one more author, where they had looked at the chromatic number of Rn with 3 distances, with 4 distances, with 5 distances, and they had some numerics, and just this kind of maximization gives you a precise value, so you get exactly so their numeric, they didn't have this exact maximization come out of their work, and so you can improve on their numerical bounds because you just have a greater precision. But the right-hand side is crude for basically any value of gamma. So why write it this way? Why write the main theorem this way? It's mainly because I wanted to, so for any specific value of m and k, I claim that you can get a slightly better bound by doing the exact maximization. And so why write it that way is because I wanted a way to express things exactly. And I specifically wanted to contrast it to the upper bound and like make it clear that we have the right order of magnitude, that we're the right order, the right growth in m. So that was like the main reason why I wanted to put it this way. And just for a general m and k, it's kind of hard to say what's going on. But yes, this bound is always worse than what you get by just calculating the maximization for a specific gamma.
I see.
But it's not, I guess you could ask how much worse it is, and I don't know the answer to that. I did not think about the second term in the expansion.
Yeah, I was just thinking in terms like if you put k like equal to m or something, then gamma will be close to 1, and then maybe you could like get a better constant.
Yes, yes. So that's a great example. In fact, when k is like if k is close to m, if they're similar, you actually do get a bound out of this method. I have to be a little careful. Yeah, you can get a bound for m close to k, but this bound is trivial. This will just be a number less than 1 to a power n. It's just not very exciting. But you can, yes, yeah. So when m is very close to k, the method still gives a bound. This maximization still gives you something, but the result I quoted is not actually meaningful there. So one has to, and that's why in my paper I put both theorems. I kind of put this one because I think it's like the cleanest. It's like this is what's going on. But if you want the higher precision, we have this result. This is, and you can just calculate it for any k and any m. And I put a table in my paper that just, because there's slightly better calculations for these numbers for m is 2, 3, 4, and so on. And I will say that, yeah, it's just one other note, because it's a problem I quite like, is when we just have the regular distance graph with one distance, all of this still applies. This is exactly how you get Ragorodsky's bound. So Ragorodsky has the best lower bound, And it's a little bit better than Frankel and Wilson's bound. So that was what I mentioned from the start. Frankel and Wilson were the first people to give an exponential lower bound. Ragorodsky improved their lower bound. Frankel and Wilson, their set S was 0, 1 to the n. Ragorodsky's set S is 0, 1, 2. And you might think like maybe you can do better with something else or a different lattice. And I couldn't. Maybe there's a way. I'm not sure how, but it is kind of interesting that there's not really a good idea that I know of how to improve Ragorodsky's lower bound. And but it's the exact same method here. So this is just like a very kind of general version of it. But you end up with, for Ragorodsky's, you end up with something that looks like the maximization of 1 plus t cubed divided by 1 plus, 1 plus, k is 1, m is 1, 1 plus t to the 1/2 plus t to the 3/2 divided by 1 plus t squared. And that maximization is just the constant I wrote above. And
yeah. Okay. Does anybody else has another question? Okay, so thank you, Eric. Thank you for I enjoyed very much actually. Let me stop recording.
okay.